Hello everyone, Dr. J here, and in this video we're going to be talking about mission planning for UAV flights. This would be like photogrammetry missions in particular, LiDAR missions or multispectral missions as well, especially photogrammetry missions though. And we're going to be talking about ground control, survey accuracy, and resolution. So we're going to talk about the different phases of flight planning, safety procedures and checklists, just general kind of preparation for a mission. We're going to talk about GCPs and how to make sure that they are set up in a way that ensures your flight accuracy meets specifications. We're going to talk about GSD, ground sample distance, how to set that up, how to calculate your overlap percentage and flight speed required for a mission. And we're going to talk about just general kind of checklists and preparation for having a safe mission. So let's get started. So throughout the whole mission process, you want to keep the main goal or aim of the mission in mind. And the idea here is that if you're not flying for fun, then there's some purpose or objective for your mission. You want to carry out a photogrammetry mission to build a 3D model. You want to collect some multispectral data to be used for looking at plant health. You want to build a 3D model using a LiDAR point cloud. So whatever your mission is, and this doesn't necessarily mean it has to be a commercial mission, it could just be, you want to build a 3D model of your house. But there's going to be a purpose for that mission. And in order to do that, you want to make sure that you'll be able to meet the objectives of your mission. You'll want to make sure that you get the proper resolution, that you are using the right kind of sensor in order to get the data that you need. Do you have a sufficient UAS to carry out the mission? So you want to define your project first. What are the specific objectives that you want to achieve? And you're going to do that by thinking about the scope of the project, the area that you're going to fly, the location, the type of data that you're going to need, the particular UAV or UAS that you're going to need, and assessing cost, labor, and time. And of course, this last point is especially important if you are actually flying commercial flights. There is a lot of flight planning software out there, and that can be really helpful for assessing these things. And we're not going to talk about that too much in this video, but maybe in a separate video, I'll talk about how to use flight planning software and to set up all these different parameters using that. One of the big things that you'll want to think about in planning for a mission is the accuracy and resolution that you're going to need. What is going to be required based on the demands of your project, and what is realistic for you to be able to achieve with the UAV that you have. So if you require a GSD of 1 centimeter, let's say, then are you going to be able to have a sufficient camera to achieve that ground sample distance of 1 centimeter? Will you be able to achieve a ground sample distance of 1 millimeter? Is that a realistic kind of objective? Probably not in most cases. But maybe in some cases you have a small area and you have a high resolution camera, then you could potentially get that 1 millimeter GSD. That would be a very unusual project. But 1 centimeter GSD might be a fairly common or realistic kind of project, but you would still need to have a high enough resolution camera in order to be able to achieve that GSD and fly at a particular height. And we'll talk about how to make those calculations in a minute. For the UAS itself, that's going to obviously probably be your most limiting factor because I'm sure most of you are not going to have like many different UAVs to choose from, and so you're going to have to sort of work with what you have. And if you're doing photogrammetry, obviously that's a regular camera. If you're doing LiDAR, you're obviously going to need a LiDAR sensor, and so depending on what you have is going to determine what you're able to do. Some UAVs are only going to carry one type of payload, some will carry multiple payloads, and some payloads are appropriate for certain types of missions, and some are not. So if you really want to get topography in a forested area, you're not going to be able to use photogrammetry. LiDAR is going to have to be the instrument that you use. One of the big things that you'll want to think about right from the beginning is what is the area of interest that I'm going to be flying and what is the coordinate system that I'm going to use. And this is going to be a little bit of geodesy here, but that's okay. We need to define the reference system that we're going to work within. Are we going to use WGS84? Are we going to use a state plane system? What's the requirements for the project? What is the requirements for the final products that we're going to generate? And what am I going to need to, for example, what coordinate system am I going to take my GCP coordinates in? Am I going to use a UTM system or am I going to use lat-long? those kinds of things. And if you do transformations, those are going to introduce some amount of small errors, not a huge amount of error, I would say, but some small errors. And so if the project has these specific accuracy constraints, you're going to have to make sure that your final project doesn't violate those constraints. And the more transformations that you do, the more you're going to have problems with that. And so identifying what coordinate system is the final project going to be in right from the get-go is going to be important. So just an example, here's a description of the Missouri Coordinate Systems Central Zone, 1983. It's a transverse Mercator projection. I'll bring up a picture here. So these are all the different state plane systems that are in use in the U.S. As of whenever I grabbed this graph. And you can see there are different directions, for example. Some of these planes are kind of more east-west oriented, some are more north-south. And those are actually different types of projections. This is transverse Mercator that's used in Missouri. And other systems use a Lambert conical transformation. So you'll want to identify if you're using state plane, if you're using a UTM zone, if you're using WGS 84, that's latitude and longitude, then what is that coordinate system that you're going to be using? And make sure that your GCP coordinates, for example, are taken in that coordinate system. Then there's planning for the flight itself. And this is going to be things like weather. What's the weather going to be like? What's the specific flight plan or flight paths that I'm going to use? What is the specific software I'm going to use for processing the data? Those kinds of things. This is going to include things like LANC requests. So is it controlled airspace? Do I need to request authorization to fly in that airspace? Now, if I'm using the LANC system, such as on the any of the Before You Fly apps that the FAA has approved, then I can do this pretty much on the fly. I can say I need to fly in this zone, and up to a certain elevation, let's say maybe only 100 feet high or 200 feet high, then I'm going to be able to fly there with that LANC authorization. But of course, if my zone only allows me to fly up 200 feet, that's going to impact what I can fly, what mission I can get. What's the size of my area? That's also going to be a very important factor. If you have a very large area, you're probably not going to be flying very high resolution, and vice versa. Can you maintain visual line of sight from one location? Are you going to need to do several flights and basically move around your area so that you're able to maintain visual line of sight of your drone in all the different parts of the area that you're going to be flying? And what's the terrain like? Do you need a special instrument to accomplish the mission? Let's talk about ground control points. These are, of course, GCPs. GCPs are points in the image with known locations. So these are flags that we put out on the ground, and then we're going to essentially tag those flags with a known location, which we get from, let's say, an RTK GPS. They're going to provide the needed reference points to georeference and orthorectify the entire image. GCPs, we can place flags specifically to use as a GCP, or if we can have, corner of a building, corner of a sidewalk, points that can be identified in photos later on and surveyed later, you can actually use those for GCPs as well. And in fact, if needed, you could actually go back and collect more GCPs using these kind of hardscaping points. So the GCPs are going to have known locations. We're going to assign the locations of those points in the photographs. And of course, there's going to be a process to do this, which is going to involve going in and picking out points in photos that you can see the flags, the ground control points, giving their locations, and those are going to be used to georeference the entire image. If you don't have georeferenced photos, then this is going to essentially be required to get a georeferenced orthomosaic or 3D point cloud, and it's still preferable even if you do have georeferenced photos, because that georeferencing is not particularly accurate. If you have RTK positioning of the drone, that's going to be slightly better, but really the gold standard is using RTK positioned ground control points tied into a local benchmark, and that's going to allow you to really accurately georeference your orthomosaics and your 3D point clouds. That's going to give you the highest georeferencing accuracy of any of the other methods. Other methods being using the built-in GPS on the drone itself. Now, what about choosing GCP locations? GCP locations need to be easily identifiable in photos, so you don't want them to be under trees, for example. They need to be things that are fixed in place, that are not movable. And we can, as I mentioned, use things that are easily identifiable from the air. So for example, we could use the corner of a fence, a point on the sidewalk where the sidewalk has a corner, maybe the corner of a building. We can use these different fixed points. Here's the corner of a table, a lot of corners. Corners are useful because it's very clear where the corner is. You can see it in the photo and you can see it on the ground quite easily. And you can survey these later on if needed. So let's say you go out and you put out 5 GCPs initially, and then you realize later on, boy, I had a kind of an area of my survey which was sort of off by itself, not really connected to the main part of the rest of the survey. That probably needs its own GCP or maybe a couple of GCPs there. Then you can go back and add those later on if you can find these hard features to reference to. Otherwise, you can use GCP flags, and this is very common. Colored to have high contrast, identifiable from the air. They need to obviously be numbered or marked to be uniquely identifiable. If you're looking at a photo, you want to know which flag you were looking at. And you're going to take the GPS coordinates of the center point of this flag. And so that's how you're going to get the position of these GCPs. And again, you're going to want to define in advance the coordinate system that you're going to use, what accuracy you're going to aim for, and what surveying equipment you're going to need to use to get that accuracy. So if you only need, let's say, 10 centimeter accuracy, then just regular GPS might be good enough. If you need 1 centimeter accuracy, your R2K GPS is going to be absolutely required. And if you need something less than 1 centimeter, you're going to need to use a total station or something like that. Actually, our handheld GPS is going to only be accurate to, let's say, on the order of a meter if you have dual frequency. And that's going to depend a little bit on the conditions, trees and buildings and things nearby. But your RTK GPS is going to be accurate. Relative accuracy is going to be around 1 centimeter. So that'll be much better. Your GCP locations need to be picked so that they cover the area of interest, obviously, but also need to be kind of around the edges, but not at the edges. And I'll just say, this is the one that you want to follow, not this one. Here you've got this area here, which is sort of separate from the other areas, and it's not really covered with GCPs. So you want uniform coverage of your GCPs around your area, but you also want to cover areas that are by themselves in a way, sort of separated from other areas. So here we've got this one area, which is covered by these 4 GCPs. We've got this area here, which is covered by these ones, and then separate areas also have a GCP, and that's going to allow you to maximize your area. But you also want to make sure that you're not right at the edge, because your GCP needs to be visible of the sky. It needs to see the sky, see the satellites, and so you don't want big trees or buildings nearby. A minimum of 5 GCPs is recommended. 5 to 10 is usually enough for large projects. If you have complex topography, separate areas, use more GCPs for those areas. But again, we don't want the GCP exactly at the edge of our mission area. Why? Because it's not going to be in that many photos. We need our GCPs to show up in several photos, a bunch of the photos, so that we can identify them in a bunch of photos. And then the software is going to use those photos. It's going to need several photos, at least 3 or 4 photos for each GCP in order to really be able to process the imagery using that GCP location. So if your GCP only shows up in 1 or 2 photographs or just a few photographs, it's not going to be particularly useful. On the other hand, if we've got the GCP marked in a bunch of photographs, and let's say we've got a bunch of overlapping photographs now, if I'm overlapping my photographs, now the GCP is showing up in many more than just 1 or 2 photographs. It's showing up in a bunch of photographs because of the amount of overlap that I have, and it's a little bit of ways away from the center, or excuse me, from the edge of my study area. So now let's talk about accuracy of GCPs, or accuracy of the GCP location that we need in order to get a particular accuracy of our image. So ground sample distance, I've mentioned this before, GSD, ground sample distance. This is the distance between consecutive pixels on the ground. And you can see how this is going to be related to the focal length and the altitude that you're flying, as well as the size of the detector, or basically the image sensor size. And so that's going to be all dependent on the camera that's on your drone and how high you're flying above the ground. That's going to determine your ground sample distance. Now, in order to properly see your ground control points, your GCPs, you need to have them visible in your images. And so you need at least 5 to 10 GSDs per size, per target of your GCP. In other words, if I back up here for a second, let me back up to where I've got my flags, right? So here's my flag, and that's a particular size. If I don't have at least 5 to 10 pixels, essentially, that is covering this ground control point, it's just going to look like a blurry spot on the ground. I'm not going to be able to really see this location, which is where I took my GPS point, in order to be able to mark that in my photographs. So I need to have at least 5 to 10 GSDs in my GCPs, if that makes sense. So for my ground control point flags, for the actual flags themselves, I need to be able to have 5 to 10 pixels essentially per flag at a minimum, and ideally even more. And I can tell you, having done this quite a lot before, that it's really good if you have really clear images of your ground control points in order to be able to mark them accurately. If you can't see them, it's going to be hard to tell which flag that you're looking at, and it's going to be hard to mark the location accurately if they're really blurry. So you want to have as many GSDs per GCP target size as possible. And then what about your GCP accuracy? So again, if you can't see your ground control point flag, how are you going to be able to mark it accurately what the position was? So you've done the RTK GPS, you've surveyed in your ground control points accurately, but now you've got to mark them in your photographs. And if you don't mark them accurately, then you're going to lose the benefit of having that high GPS accuracy. And so your GCP accuracy in your final image, or for your final image processing, is going to be around 0.1 GSD. So a tenth of your ground sample distance is as good as you can get for your ground control point accuracy. Now let's talk about flight planning and mission planning from the perspective of actually designing your flight. If we have, we've seen this diagram in other videos. Here's our camera located. Here's our image sensor here with width W. There's our focal length F. Here's our ground image W. And the height of the camera above the ground is given by H. And sometimes we'll call this H prime. So this is H or H prime, depending on your terminology. H prime, just distance above the ground. So given a camera, a scale, and an overlap percentage, the distance between photographs taken and the distance between successive photographs is fixed. And basically, because we have this relationship, which we've talked about before, let's see, how does this go? It's H over W. It's supposed to be a W there. Is going to be proportional to, and this is going to be, so H is my height, so that's going to correspond to my focal length. And then that's going to be over the sensor width, so little w. So H over, that's supposed to be a big W, is going to be equal to focal length over little w, sensor size. And so from this relationship, we can work out how far apart the camera needs to be in order to have a particular overlap, or how much overlap we would have for a particular distance between cameras. So we can go back and forth between these notations. By having 3 of these 4 parameters, we can work out what the others are. And typical 60 to 80% front overlap is typical for high precision UAV flights, and also for side overlap, depending on what you're doing. If you're only doing orthomosaics, you don't need as much. If you're doing 3D models, then you definitely need a larger, higher rate of overlap. So again, here's our side overlap now. And we can also calculate that in the same way as the others. And let me just give you some example numbers here. So 75% front and 60% side overlap in general cases is the recommendation from Pix4D. So Pix4D recommends 75% front overlap, 60% side overlap for general cases. 80% frontal and side overlap for agricultural fields. That's where things aren't changing very much, right? We just have crops, and the crops look similar, and so they recommend 80% both frontal and side overlap for that situation. 85% front and side overlap for forests and dense vegetation, where you're really trying to get that 3D information. You use a lot of overlap. And for corridor mapping, they recommend 85% frontal overlap. And if you're doing 2 flight lines to map the corridor, then use 60% side overlap. That's from Pix4D. There's some other folks that have other recommendations. Erotus recommends 75% and 75% for both front and side overlap, which is with values that are a bit higher for dense forest or tall buildings and agricultural fields. So same as Pix4D, use a bit more overlap for either very featureless areas or for forests and buildings, things that need a lot of 3D information. All right, let's do an example problem. We've got 2 ground control points. They're both targeted to appear in aerial imagery in a particular photograph. Their coordinates are given there in that top table. The photo coordinates are given in the bottom table, and the focal length is 152.265 millimeters. What is the flying height? So here we're going to use this relationship which we saw before. We're going to use the relationship between focal length, image sensor size, ground distance, and drone height. And this is sort of illustrating the photogrammetric process. The photogrammetric software is going to solve for the camera location given information about the photos and the ground control points' real-world locations. So we've got the real-world locations for some ground control points, and we're going to use that and the camera locations, the locations of those ground control points in the images to calculate the location of the camera. Now, in this case, we're just looking at the height. In reality, we'd be looking, well, in reality, the photogrammetric software solves for the 3D position of the camera as well as its orientation. But for now, let's just look at this height problem. And so what do we want to do is we want to calculate the distance between these points on the ground, the distance between these points in the photo, and then we'll use that mathematical relationship that we had before. So the distance, I've done the calculation for you, but if you want, you can pause the video and work that out yourself. So the distance between these 2 points, T101 and T102, we're going to take the square root of the difference of these numbers squared and then add them together. So we'll take the difference between the northings, square that, add to that number the difference between the eastings squared, and then we're going to take the square root of the sum. Then we're going to take the difference of the position in the photo coordinates. We're going to take this number minus this number squared, plus this number minus this number squared, and we'll get the distance in the photograph. And then we'll use those 2 distances as our numbers in that ratio that we saw before. And what was that ratio? I think it was H over W. H over capital W is equal to the focal length over little w. For whatever reason, I can't draw a big W. That's supposed to be a big W there. And so that's the height of the drone above the ground, which is what we're solving for, divided by the distance between the points, the ground control points. That's going to be given by this. Actually, we don't need this elevation part here. We're just going to take the difference in the northing and easting because it's the projection of the distance onto the XY plane anyway. And then we're going to take our focal length and our sensor width. There's our focal length given there. And sorry, not the sensor width. This is going to be the distance between these 2 pixels there. So we'll take these numbers, and I've done the math here already, but like I said, pause the video and work this out yourself. First, we've got the square root of, what's this going to be? Negative 528.23 squared plus negative 2574.15 squared. That's going to be the square root of a big number, 6905275.15. And that's going to give us a final distance between these 2 points of 2,627.79 feet, approximately. And then the distance between the photo coordinates, we're going to go through the same math, square root of the sum of the squares, squared differences, and that's going to give us 137.82 millimeters between these 2 points in the photo coordinates. So we've got 137.82 millimeters for this distance. Focal length, we already know, is 152.265, so we're going to divide those 2 numbers, and then we're going to multiply by the distance between these 2 points, which is this capital W here. We'll cross-multiply both sides by capital W, and that will give us the H, and that H is going to work out to be 2,903.21 feet high. So our drone is flying 2,903.21 feet high. Now, in this case, this is probably not a drone. This is actually probably an aircraft, a manned aircraft, which is flying that high because we wouldn't be flying a drone that high. But the same principle applies to the photogrammetry problems. Here's another example problem. Let's talk about ground sample distance, GSD. We need a GSD of 1 centimeter required for our mission, and the camera focal length is 150 millimeters. The image is 2500 by 2500 pixels. Sensor width is 2.5 centimeters. So that's our little w that we've been working with. That's supposed to be a little w there. There's our focal length. That's 150 millimeters. And then we have 250 by 250 pixels on the ground. So there's 250 pixels across this distance. We've got our flight height. No, we need to get our flight height. What flight height is required to meet this GSD requirement? So we're going to do the same kind of process. We've got this distance f is going to be proportional to this distance. This distance focal length over w is going to be proportional to flight height over our ground distance. Okay, so the ground distance, we need to know what our ground distance is in order to divide that up into 2,500 pieces, and that will give us our GSD requirement. And what we have now is the flying height h is going to equal the focal length f, and I'm going to multiply that by the number of pixels n, and I'm going to multiply that by the ground sample distance that we want, and then divide by the sensor width. So there's our focal length, there's the number of pixels across there, and our ground sample distance that we want. So this n times our ground sample distance should equal the total ground distance here. And f over w, focal length over w, should equal, focal length over w should be the same as flight height over our ground distance. And so here's our focal length over w, and that should be flight height over ground distance, and we can cross multiply. So there we have it. So this expression now allows you to work out what flight height you need for a particular ground sample distance, image, camera parameters, and here's our image size, and this is the height that we need. And so if we plug in the numbers from our description here, we'll end up getting a flight height of 150 meters. So 150 meters is almost 500 feet. So we probably wouldn't be able to fly this mission with this GSD. We would probably have to fly a bit lower, but actually a bit lower would give us, if we needed a GSD of 1 centimeter or less, then we could fly right at 400 feet, and we'd be able to meet the requirements of our mission. All right, let's do one more example problem. These are good for us to think about and help us kind of put all these different topics together in our minds. We've got a camera with a sensor size of 2.5 centimeters, so that's our little w. That's right there. And a focal length of 100 millimeters. So again, we've got this, and this is what often happens, right? We have a camera, we have a particular camera, and we want to design a mission to fulfill certain requirements. So we often have the camera parameters, and we're trying to use the other parts of the mission, the flying height, the speed at which we're flying, and how often we're taking photos. We're trying to use those parameters to get to the mission parameters that we need for our mission objectives. So I've got a flying height here of 100 meters. That's our h. And what should the picture spacing be? How far should this distance be for a 75% frontal overlap? So we're flying along, we want 75% overlap between images. How far between, our drone is flying along, how far between pictures, how far should each picture be apart? How far apart should each picture be? So we're flying along with our drone taking pictures, how far apart should each picture be in order to get a 75% frontal overlap with these other parameters? So again, we're trying to design our mission, given a particular camera, we're designing our mission to fulfill our objectives. We want 75% overlap for it. Okay, so here again, we're still using our same ratios that we were using before. We've got H over capital W, capital H over capital W is equal to focal length over little w, that's our image sensor width. And here we've got a 100 meter height. So we're not solving for that, we're actually solving for this, we're not solving for any of these. What we're solving for is this distance b, and you can see here b is going to be equal to w minus the overlap region. So what we're going to do is we're going to solve for what W is. So if we have a 100 meter flying height, a 100 millimeter focal length, 2.5 centimeter sensor size, then our width, our W, is going to equal 25 meters. So this is going to be the ground distance, W ground distance of each image. We'll have a 25 meter width. We want 75% overlap, so 75% of 25, that's going to be 18, about almost 19, 18.75 meters. So we want 18.75 meters of overlap. That's going to be our overlap region. Then to get B is going to be 25 meters minus our overlap region. And so we're going to end up with a 6.25 meter spacing between pixels. So every 6.25 meters, we want to take another image. If we have a fixed drone speed, then we know exactly how often we need to take those images. Okay, so let's just talk about some general things about flight planning. AOI assessment in the field. This is where you go out to the field, and I do recommend this if you can. Check out your area that you're going to fly prior to actually flying. Ask local residents about activity. Make sure you have, of course, permission to fly where you're flying. Permission is actually a tricky one. Maybe I'll just say something about that real quick. Because of the fact that the FAA governs airspace, there is a debate right now about who is able to sort of control what happens in the air above their property. So you need to be very, very careful about flying over people's property, even though right now, technically speaking, the law allows you to do that. It's actually debatable. There are court cases going on right now as I record this video about whether or not private residents, institutions, organizations can control the airspace above where their facilities are located. And it's not clear what's exactly going to happen with all that. So just be very, very careful about flying over places, and make sure you get permission for flying over those places if you're flying over areas other than where you're taking off from. And obviously you want to do your terrain check, look for obstacles, look for towers, and if you look at my videos on airspace charts, aeronautical charts, then that's going to help you with that assessment. You'll want to obviously check the weather. You're not going to be able to fly in the rain, most likely. You're not going to be able to fly in the fog. You're not going to be able to fly in conditions where you're outside the manufacturer's specifications for the UAVs.
Yep.
So here's an example. I have a DJI Mavic 3E, and it gives you very specific weather conditions for when you can fly. So don't fly in wind speeds 12 meters per second or above. So don't fly in wind speeds 12 meters per second or above. Do not fly at altitudes above 6,000 meters. Don't fly in snow, rain, lightning, fog. Don't fly in below 10 degrees C or above 40 degrees C conditions. And don't fly in specular reflective areas such as water or snow to ensure proper operations of the visual positioning system. So there's all these conditions that each drone is going to have, and you'll be able to see that information from the manufacturer. What are the weather conditions that I can actually fly in? Is it too hot? Is it too cold? Of course, regulation in the US requires visibility of at least 3 statute miles. And so if you have visibility less than that, you're not going to be able to fly anyway. And obviously, if you're flying a custom drone, then you're going to need to use caution and figure out what are the conditions that your drone can actually fly in. Now, there are other kinds of obstacles besides just physical obstacles. You can have electromagnetic interference from radio towers or power lines. I think some drones have gotten pretty good at avoiding electromagnetic interference, but you may lose radio control. And if you lose radio control, your drone could fly off and end up who knows where. So you want to be very careful about that. Also, just something to be aware of is that the drones are using Wi-Fi broadcast frequencies to connect the controller to the drone. And so this is the same frequencies that Wi-Fi hotspots and routers use. And so this is something, again, you'll want to be very careful if you're flying around a strong Wi-Fi source, cell phone towers, things like that. That's going to potentially cause interference with your controller and could lead to problems with your drone flying off. Now, as we talked about in other videos, you cannot legally operate over human beings without a waiver. You also cannot legally operate over moving vehicles without a category drone or a waiver. So you're going to need to make sure that your mission is able to be carried out given these restrictions. You're going to need to be able to fly without flying over people. And if that's not possible, then you're going to have to try to get a waiver or get a category drone, something like that. And again, maintaining visual line of sight. How are you going to be able to maintain visual line of sight? Do you need to move around? Do you need to break up your mission into small segments? All of that you want to plan out ahead of time before you actually go and fly. And just one final recommendation, the use of checklists is really helpful for this. These checklists you can find online, find examples. I'll put some links in the notes to this video. Checklists are going to be really helpful to just help you walk through all of these ideas and concepts every time you go out to fly. So all these things are important to think about prior to going out to fly, and a checklist is going to help you think through all of these things. All right, so that's it for today, and I will see you in the next video.